Um, Lino, since there are no English speakers, you can give a talk in Portuguese or Spanish if you choose, but you can also do it in English. Up to you.
I don't know
Um,
what. Maybe I'm not sure if the people prefer it in English or not because my Spanish is. I'm also equal with my English is. The both are bad, but I'm not sure.
they are very similar to each other, right?
Exactly,
Anyway,
exactly. It's the same equivalence class, but
Yeah.
um,
If you speak,
I don't
so
know.
sorry. If you speak
Sorry.
in Portuguese, if you speak in Portuguese for a Spanish, it's okay, okay. For a Spaniard, right? For a Chilean, right? If you speak in Portuguese, si hablas en portugués para
Okay,
un
okay. I
chileno,
see.
tudo va bem, okay?
I see. Okay,
but
but
that's just
for
for the Chileans because they are very smart. No, but just Lino, hold on a second. Please put your please put your talk on please start sharing your screen. Just to
okay,
remind everyone, if you're here for the first time or if you've reconsidered joining our mailing list, so to subscribe to the geometry webinar, you can send the word webinar to geodiff@unicamp.br, or you can WhatsApp it to the number on the chat. You can find it on the chat. Also, the future calendar and previous recorded talks can be found on the same chat. So don't hesitate to get in touch. Uh, um, Today, I'm very happy to have my very own colleague here at Unicamp. Lino is also a protagonist in the local differential geometry group. We do lots of stuff together, but uh, 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 I, now it's time to work on this South American seminar together. Even he doesn't know that yet, but it's going to be asked. And telling us about invariant Einstein metrics on real flag manifolds. So, Lino, we're doing this 50 minutes and then 5-minute questions.
okay, great.
Is that good?
Okay,
Okay.
okay,
And if there are any questions, people can interrupt or they can send them via the chat to me, and then because Lino cannot read the chat, so I
okay,
will pass on the questions to you. Okay?
okay, great.
Very good.
Okay, okay. Thank you, Enrique. Thank you very much for the organizers to invite me to speak here in this geometry webinar. And very nice to see a lot of good fellows here. And I hope everything is good with all of the people in the Chile, Argentina, Colombia, etc. In Brazil, of course. Okay, and today I start to talk about it's a joint work with my friend Brian Grajales, and the results report here today is available on archive in this prepping. Our goal here is classify the invariant Einstein matrices in a family of the homogeneous space we call real flag manifolds. And today we work in the associated to classical Lie groups. Okay? And Einstein matrices is a very famous subject in differential geometry, is equivalent to find the solutions for this equation, they call Einstein equation, and we're looking for matrix G where the which tensor is proportional to metric G. To this guy. Okay, and the problem is given an homogeneous space, find the G invariant matrix that satisfy the Einstein equation. Okay, and this is even in the homogeneous case, in the invariant here, it's not an easy problem. And in the general existence or non-existence results are very high, and there's a very deep results also. And I just quote some very few cases here, but it's remarkable work of the Wang Ziller. This is a very classical work now. is about the existence or no existence of Einstein metric and the homogeneous space. Of course, here we are interested in to know if there's some solution for Einstein equation, but not solve the Einstein equation properly. Okay, I just look the homogeneous space, find some invariants, and decide if this space admits or not invariant Einstein metric, but not to solve explicitly a priori the equation. Because of course, if you solve the Einstein equation, you can find the solution. But here is some just if it exists or not exists invariant Einstein metric. More recently, there's the work of Christoph Bohm. Oops. There's a lot of deep results here, and Bohm associates to homogeneous space simplex, and analyzing the topology of the simplex, you can decide if there exists some Einstein metrics, invariant Einstein metrics, yes or no. And there is another remarkable work here by Bohm, Wang, Ziller. This time there is a paper, validational aspects of invariant Einstein metrics. There's a lot of results, but just quote one here is about given an homogeneous space, you can associate a graph, and then analyzing this property of this graph, you can decide if this homogeneous space that admits invariant Einstein metrics, yes or no. And then some examples here. Of course, here is a very incomplete list, just to quote some results. But this, for the classification of the invariant Einstein metric in spheres in projective space is due to Ziller, long time ago. I would like to quote this result by Alexevsky, Dotti, Ferrari about the 5-dimensional homogeneous space. They classify the positive heat curvature and Einstein space in this work. We have several partial results on Stiefel manifolds. This is due to several authors, but in this case is some families of Stiefel manifolds. In many cases is solved by solving the Einstein equation. We have some classification in families of complex flag manifolds. This is due to several authors. I will quote some of them in a few minutes. And then this is a very interesting result too. Is due to Christoph Bohm and Megan Kerr. Up to dimensional 11, every compact simply connected homogeneous space admits an invariant Einstein metric. And due to an example in the same paper here by Wang Ziller, this is the best. This is the best situation. I mean, in the dimension 12, there exists a simply connect homogeneous space that is no admit invariant Einstein metric. Okay, and this is the best one. This is the hypothesis here. The simply connected is essential, as I show in an example in a few minutes. Okay. By now, I just would like to introduce the family of the homogeneous space that will work. Is they call the flag manifolds. But now we split into two types of the complex flag manifolds and the real flag manifolds. Okay. These are family of the homogeneous space, and why this family is interesting to study. Okay. This homogeneous space in this family are described in terms of the Cartan-Killing classification of the complex simple algebra, like symmetric space. I mean, for symmetric space, you have a symmetric space of type A, type B, type G, exceptional the group type G, type E, type F, and so on, etc. For complex manifolds and the real flag manifolds, we can do a similar classification. We have complex flag manifolds of type A, type B, type G, and so on, and the real flag manifolds for this type of the complex simple Lie algebra. And the definition of complex flag manifold, and I spent some time now and comparing the complex and the real flag manifolds, just to put some perspective. The complex flag manifold appears in the literature as scalar C space. Is that the same? Is a homogeneous space G over P, where GC is a complex simple Lie group, and P is a parabolic subgroup. Okay. We can take the compact real form, we call U, and this U also acts transitively on the flag manifold, and we have this identification. And here is a very, very well-known example. Okay, for type A, we take this simple Lie group, take the parabolic subgroup now is the Borel subgroup, upper triangular matrix, and we consider this homogeneous space. This is called maximal flag manifold. And if you consider the compact real form, is a SUN. And in this case, this intersection is the torus. And we have this identification. Okay. And this manifold is very, very well known. There's a lot of geometric properties. For instance, if you look for Hermitian geometry or almost Hermitian geometry, or you can use this. Or if you're interested in Riemannian geometry or symplectic geometry, you can use this site. And now, real flag manifolds is a similar description, but now we use the split real form of the complex Lie group. Just to recall the definition, real form of the complex Lie algebra G is split if for every Cartan decomposition there is a Cartan subalgebra A inside S. Oops. Okay. In this case, we have very similar description in terms of roots, simple roots, root space decomposition, parabolic subalgebras, etc. And we can, for the point of view of Lie theory, we can handle of this in a very nice way. Okay. Our example for today is we visited this example several times. But we consider the SL, the real here. Okay, is a traceless matrix over the reals. We can consider this Cartan evolution here. The compact part here is SOL plus 1. And the part S we call G is K plus S. Sorry, here. Okay. In this case, this K is the SO. And the symmetric matrix here is the part S. The people here is probably we will recall this from the Cartan evolution and the composition between the +1 eigenvalue, -1 eigenvalue for this Cartan evolution. In this case, the Cartan subalgebra is the diagonal matrix. It's very similar here to the complex situation. We define this lambda is just the projection here. We define the set of roots by this family of functional, and the simple roots here. This case is completely identical to the complex case. Okay. This is the Cartan killing for, and we can define the parabolic subalgebras is completely similar to the complex case. Okay, we have the Cartan subalgebra, positive roots here. This is the sum of the root space, and here is negative roots spanned by this set of simple roots. Okay. If you don't understand this part of the theory of root decomposition, root space, don't care about for now. As you just need to recall this. For every subset of simple roots, we can define one parabolic subalgebra. This is the most important for now. And the definition of real flag manifold is now, for the split real form, is similar to the complex one. Is the group G model over the parabolic subgroup determined by this theta. Okay, and the theta is a choose of the simple roots. Okay. We can also consider the group K associated to this algebra, K, in the Cartan decomposition. And this group also acts transitively on the flag. Okay. And in this case, the isotropy subgroup is given by this K theta is just this intersection. Very similar to real for the complex case. Okay. And in many cases, we just consider this realization of flag manifolds, okay, for the real flag manifolds. Just for recall, I'll be back in this isotropy representation in a few minutes, but just to put some more definition here, if you consider an homogeneous space M, and we call the origin O, the point O, is the trivial coset, and the isotropy representation is a representation of the group H, the isotropy subgroup H, on the tangent space at O, at the point O. Okay. So, and this representation is induced by the differential of the G action on N. In a few minutes, I'll back to this point and in a more precise statement, but for now, we just need to keep with this. We have some representation here. Okay. From maybe called this rho. Okay. And then this representation is induced by the G action on the homogeneous space. Okay. And for the complex manifold, is a very important ingredient to this isotropic representation because this is completely reducible, and we need to understand how this vector space decompose and sub-representation in this case. Okay, and in complex case, this is a valued result by Siebenthal, the Siebenthal, in 1966. First, in the complex case, the tangent space at the origin can be decomposed into irreducible and non-equivalent components. And in this case, we have the following decomposition. Okay, but the most important here is, and this is the sum of the at the theoretical level. The most some of the very important difference here between the complex and the real case is the following, because for complex case we have non-equivalent components, but in real case the representation is we can decompose it completely into irreducible components, but equivalence between these components can occur. Okay, we can have some equivalence between these components. And the complete description of the irreducible components and its equivalence is not as a result for 2050. Okay, just 5 years ago. And, in this case, after this result, the people start to study more invariant geometry in this family of space. Just to put more concrete situation here. Okay, let's consider the flag of the SL4. In this case, we have this set of simple roots. You have 3 roots. Just remember, we are in the real case now. Okay, the notation we keep the same, but just to keep it in mind is okay. And we call the flag are described by this capital theta. Okay, and if you choose a theta, we can produce in a parabolic subgroup, and we just take the mode out of G over the parabolic subgroup determined by capital T. And if you choose theta is empty set, you have this homogeneous space. This homogeneous space has 6 irreducible isotropy components, and we have 3 equivalence classes. These components are pairwise equivalent. If you choose theta is just one root, say alpha 1, we have this homogeneous space. And we have 3 reducible components, but 2 of them are equivalent. It's the similar here for the other 2 roots. We just switch here the O2 in O1 and O2 with this O1. Okay, just permute this position. And if you choose theta like this, we take this homogeneous space, or other option here is alpha 1 3. Sorry, here 3. We have this. Oops, sorry. Is 2 3. Okay, and this homogeneous space is one reducible component. And finally, if you choose this, we have this homogeneous space, and then this is 2 non-equivalent isotropy components. Okay, and this is the flags of SL4. Okay, this is so now let me recall some results of about complex flag manifolds. Okay. The first is the complex flag manifolds always admit invariant Einstein matrix. This is the so-called invariant Keller-Einstein matrix. Okay, these are Einstein space. The complete description of the Einstein matrix in a complex flag manifold is an open problem. Just to put some examples here, if you consider these flag manifolds SU3 over the two torus, this is a very famous 6-dimensional homogeneous manifold. We have actually is 4 matrices here. There is a typo here. I can fix this now. It's 4 matrix, invariant matrix. Of course, here it's I counted some isometric metrics, right? I not discount here. Okay, keep in mind here, right? And if you consider SU4 over this maximal torus, you have 29 matrices. SU5 over T4, 364 matrices. SU6 over T5 is at least 600 matrices, where this star here is a computer experiment. Okay, that is not true. It's just solve the Einstein equation by this is a computational methods like Newton methods and etc. This is not so. Is a kind of proof, and that's a conjecture that the invariant, the number of the invariant Einstein matrices is finite up to scale. And but we have some partial results on invariant Einstein matrices on complex flag manifolds, and this is done by families. We can classify the invariant Einstein matrices in families of flag manifolds, and these families are parameterized by the number of the components in the isotropy representation. Okay. I mean, for instance, let's just consider just the flag manifolds whose the isotropy representation decomposed into 2 pieces. Okay, these are the result was provided by Avarnito Yorgos and Chrysikos in 2011. And okay, we call this is a complex world. And the result is the following. These are all manifolds, all flag manifolds, complex manifolds with 2 isotropy components. And each homogeneous space in this family admits 2 invariant Einstein matrices up to scale. Okay, and this is a not so bold result. These are for 2 components. For complex flag manifold with 3 pieces here in the isotropy representation. Okay, this is a work out by Kimura in 1993, and now we have 2 types of flag manifold with 3 components. We have type 1 and type 2. This is the list of the manifolds. And the theorem is the following. In type 1, the flag manifold admit 4 invariant Einstein matrices, and the type 2 admit 3 invariant Einstein matrices. I can put here 4, 3. Okay. And now, this is the our result here. We are going to study Einstein matrix on real flag manifold. Okay. And we provide a classification of the real flag manifold associated to classical Lie group with 2 and 3 isotropy components. Okay, because the two results I quoted before, that is a two pieces. One is the classification of this homogeneous space, describe this family, and another is describe the Einstein matrix. Here is the same. Okay, we are going to show this. We have the both contribution here. One is describe this family, and another is describe this matrix. Okay, we don't need this for the 2 and 3 isotropy components, but for now it's just for the classical Lie. Okay, and this is our first result. This is the classification of real flag manifolds with 2 isotropy components and the Einstein matrix. Okay, let's see this table. Okay, the first is note here we don't have equivalent component. Okay, for the 2 isotropy components is behavior like the complex case. Okay, we have some normal metric here are Einstein. Okay, and we have some situation here is no invariant Einstein metric here. Okay, this is the first difference between the complex and the real case. Okay, for complex case, always we have some Einstein metric. For this homogeneous space, compact homogeneous space, is we don't have invariant Einstein matrix. If you consider L is equal to 3, we have some 6-dimensional homogeneous space, I guess. It's not true, but it's a low dimensional. It's low dimension is less than 11. Okay, if you recall the result in the beginner from Bond and Kerr, that is a hypothesis here in the simply connected homogeneous space. Okay, but this is not the case. Okay, this is not simply connected homogeneous space. Okay, and you have some strange behavior here. It's not the same like in the complex case. The complex case is all the way is 2 Einstein matrices. Okay, here you can change it for depends on the homogeneous space. Okay, and for 3 isotropy components. Okay, now we have some equivalent components. Okay, and the number of the Einstein metric here is can change. This is up to 4. But depends on the choice of your L. You can produce 1, 2, 3, or 4. Okay, and it's the same here, and here. Okay, and we have some normal Einstein metrics. And it just depends on the family here. Okay, and if you compare now from the real world in the complex world, you have some difference here in the geometry of this family of this this homogeneous space. Okay, but I would like just to point out here is this studies we are interested in studying this in family. Okay, it's not just picking an example in the workout. No, we'd like to put this more conceptually in terms of Lie theory, in terms of the Cartan decomposition and the root space decomposition, etc., etc. Okay. Just make some comments about the how to proceed this classification. Okay, and this is our big deal, and I guess a lot of people here watching this is how to translate invariant geometric problems in algebraic problems. Okay, We consider the smooth G transitive action and the associated infinitesimal action. We pick the point P and consider the isotropy subgroup. And of course, here is, we have this equivalence between the homogeneous space and the coset space. And we can identify this tangent space at this point P with this cosine vector space. And now, here is the precise definition of the isotropy representation. Okay, is that the differential of the G action at an element gamma in H. Okay, and this is the fixed point of this isotropy point. Okay, and we have some well-defined linear transformation here. And this is a definition we call the homogeneous space reductive. If we have this split of the Lie algebra, and the subspace M is invariant by the adjoint representation of H. Okay, if your homogeneous space is reductive, we can identify the isotropy representation with this. This is a very useful, okay? This is a very useful argument, okay? Because we can deal with this in a more appropriate way. And this is the receipt of the how to translate the invariant tensors in a homogeneous space to linear algebra problems, okay? And if you consider invariant tensors here in your homogeneous space, you just need to consider invariant tensors are on the vector space M, invariant by this representation. For instance, if you look for invariant matrices on the homogeneous space, you just need to consider invariant inner products on N. For K invariant forms, you just need to look for K forms invariant here. If you look for the almost complex structure on homogeneous space, you just need to look for endomorphism on M, such that the square is minus identity. And of course, you just need to preserve this invariance here, etc., etc. Of course, that is a very good expert here to know this. And if you look for invariant geometric flow, you need to do some analysis on ODE. And in your case, to find the invariant Einstein matrices, you need to solve some nonlinear algebraic system of equation. Okay. And if you keep this in your mind, for describing the invariant Riemannian matrix, you just need to look for the invariant inner product. And this is the Cartan-Killing form. In an invariant product G is equivalent to this guy. Okay. And this is the seminar. Okay. If you look at some invariant Riemannian metric on the flag manifold, this is completely determined by this operator A, and this operator is from this vector space, and they commute with the adjoint representation. Okay. Now we just we start to deal with the real flag manifolds. And an important step here is how to describe the invariant inner product here. Okay, and this is the proposition. No work. In this case, we just need to understand the operator A for M to M. Okay, and that exists in a base here. This base is adapted to the isotopic decomposition and to the equivalence between these components. Okay. And our operator here is the block diagonal, and inside the diagonal we have this for, where this mu is positive, and this parameter B must satisfy this relation. This is comes from the Cauchy-Schwarz for the inner product. Example. Again, for flags of SL4, how it looks like an invariant metric in this space. Okay. For the theta empty, if you recall, we have 6 components, and they are pairwise equivalent. Look like this for the two blocks here. Okay. And in this case, our metric depends on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 parameters. For the other flag manifolds, we have just no equivalence in we have 3 pieces, but 2 of them are equivalent. And we have this parameter. For this manifold here is a isotropic reducible. Okay, that is just one piece of the vector space. And if you look at representation space here, no invariant subspace here. And if you look at this manifold, you have 2 pieces, non-equivalent. You have 2 parameters, just 2 parameters. And about the classification, okay, the first step is describe the rich tensor and the scalar curvature here. Okay, this is a very classical formula for the homogeneous space, but there is some work to describe this here. And okay, once you have the rich equation, the Einstein equation, sorry, we will describe the rich tensor, you can write the Einstein equation. If the isotropy representation has no equivalent components, we try to solve this directly, but in general, this is not easy. Okay, and sometimes it's very difficult to solve directly. And we can try to apply some techniques here from try to handle this equation. For us, we use some criteria from Wang-Ziller in order to obtain the information about the existence of the invariant Einstein metric. This is the Wang-Ziller result. Okay, if you have your reducible, the isotropy representation decomposed in 3 pieces, but now you need to be inequivalent and irreducible. And Einstein metric of volume 1 is Einstein if and only if it satisfies the scalar curvature satisfies this equation, and this allows us to instead you solve the system of 3 equations. You just change the variables and solve in 2 equations. It's much better. If the isotropy representation has equivalent summands or equivalent components, we needed to compute the rich components and compute the eigenvectors of the operator A. Okay, and if psi1 and psi2 are eigenvalues of the operator A, the Einstein equation implies this equation. Here are eigenvectors associated to psi1 and psi2. And using this equation, we can obtain very strong conditions to the metric A, operator A, to be Einstein. And this approach was used by Alexeevich, Dot, and Ferrari about the classification of simply connected homogeneous space, homogeneous Einstein manifolds in the dimension 5 in the positivity curvature. Okay. And again, example, in SL4, invariant Einstein metric on this homogeneous space. This is just we can write the Einstein equation and you arrive just at the normal metric, just the 2 parameters and both are equal. Mu1 is equal to mu2. For this homogeneous space is more interesting here. You have the invariant metric depends on 4 parameters here. Okay. And the metric A is Einstein if and only if this parameter satisfies this property, sorry. Okay, and then you have some B is equal to 0. You have the diagonal metric. It's similar to complex case. But if you have some B not 0, it's allowed, but you have some other parameters here. Okay? In this case, you can produce some no-diagonal Einstein metric. Okay? Of course, this cannot happen in complex case, because in complex cases, you have just diagonal metric. Okay? And that's it. Thank you.
All right. Thank you, Lino. Perfectly on time. Have you got any questions for Lino? Or comments? Or maybe curiosity about what's happening next? Maybe, yeah, that's my question, Lino. So what's coming next in this? So you got this classification for these guys with 2 and 3 irreducible components, even if they have some multiplicity, right?
Yes.
What's happening next? Are you just looking for folks with more components, or where are you taking this from here?
Okay, this is the first step to understand the geometry of the family. Okay, we keep study this family. Okay, for instance, okay, if you can start to looking for more Einstein metric in another families. That's right. Mm-hmm. Okay, this is a lot of people doing this, but we can, for instance, study now curvature properties of this homogeneous space, or another in geometric structure. For instance, Bibiana, I guess Bibiana is also here. Bibiana, Luisa Martin, and Ana Cruz classify the almost complex structure in this family, okay? In the family of these real flag manifolds, okay? And virtually, a lot of things is done by the complex case you can do by the real case, okay? Even some geometric flows too, okay? And this is the geometric flows, for instance, okay?
So can you then classify other geometric structures? I mean, I'm very part. What about the exceptional ones? What about G2 and spin 7 structures?
Okay, this is a work in progress. Okay, this is in progress just to complete this list, but there is technically is the same. It's not so
right.
But probably some system is a little bit harder to solve, but technically is the same. But
so
this is in progress. Sorry?
Right, G2. I'm particularly interested in G2 structures.
I see.
And spin
if I found some interesting thing, I tell you. Okay.
Yeah, absolutely. Okay. Any questions or comments? Okay. If not, then let's thank Lino again, please. Okay, and we'll then meet each other next week, this time on Friday.